Thank you, Steve. Thank you for inviting me. It's a pleasure to be here. I'm a guy that always wanted to have a career in space. Wanted to grow up and be a part of the exploration of something a little bit larger than life. And this morning I'm going to talk to you about my favorite space project. I've been involved in 26 space projects in my career, ranging from suborbital missions to shuttle missions, missions that have orbited the moon and Mercury, Venus, Mars. But New Horizons is something completely different, because unlike doing something again, even to learn new things, New Horizons is a mission of raw exploration. It's going farther, and it's going faster than any spacecraft ever has. And it's going to make history in a variety of different ways. And I hope it's going to be a touchstone to excite people next year, not just about space exploration, but about what this country can do when it's on its game. This is a picture of the launch of New Horizons in 2006 aboard a massive Atlas V, about the size of a downtown building here in Manhattan, 227 feet tall, with a small spacecraft not a lot bigger than one of these two tables. Very highly miniaturized spacecraft with much more capability than we've ever sent on the first reconnaissance of a new planet ever before, using 2000s technology rather than 60s or 70s or 80s technology. And it's speeding to its destination now, 8.5 years en route on a 9.5-year journey that will culminate next year in July. And it's easy to remember when we're going to arrive. It's Bastille Day. The French are throwing a holiday. They're going to shoot off fireworks. They're going to celebrate the storming of the Bastille, and we are going to storm the gates of Pluto. Now, the question is, will this video work? Hey. This is the launch of New Horizons in January of 2006. Can we dim the lights? Yeah.
8, 7, 6, 5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit planet Pluto and then beyond. Less than 15 seconds. Everything continues to look good as the atmosphere is moving the climb to Lake Florida's coast. The 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
Well, if you've never been to a rocket launch, I really have to encourage you to go see something like that. Come down to the Cape, you pay your tax dollars, you can go to NASA launches. It's not very often you see something the size of a downtown building take off vertically. In that case, go supersonic in 28 seconds. Picture that. It took us 17 years to do that, from the time we first conceptualized the idea until we raised the funding and built the spacecraft and got it to the launch pad. It's from 1989 to 2006. And for those of you involved in business or other propositions other than research, which is where my career has been, it's a testament, I think, to the people who were involved. We survived 5 different cancellations. We had 6 restarts, 17 years. It's all about persistence. You got to really want it. And we are off on a grand journey, 3 billion miles across the entire expanse of our solar system. New Horizons launched from the Earth. Whoops, that's not going to work. There we go. Is this a point? Maybe. That's the point. So there's the sun. This first circle is the orbit of Jupiter. You can't even see the orbit of the Earth down there, way down by the sun. Jupiter's 500 million miles away, and it's the first thing that shows up here. That's Saturn's orbit, Uranus's orbit, and Neptune's orbit. There's Pluto, this yellow one. It orbits in this vast region called the Kuiper Belt. It is the third zone of the solar system. Beyond the terrestrial planets lie the giant planets, and beyond the giant planets is the Kuiper Belt. We used to talk about the giant planets as the outer solar system, but we know now, because of discoveries in the 1990s and 2000s, that really the giant planets occupy the middle zone of our solar system. New Horizons is, in a real sense, the first mission to the real outer solar system. The largest zone, the largest structure in the planetary system. First hypothesized by Gerard Kuiper and other astronomers in the mid-20th century, but far beyond the technology of the times. It took to the 1990s, development of fast computers and CCD detectors at the back end of large telescopes, that we could discover something profound, that the entire map of our solar system that we had, that all of you learned in grade school, was wrong. It was limited by our technology and our ability to see farther. It's as if we had a map of the Earth that until the mid-1990s didn't contain the Pacific Ocean, the largest structure on this planet. So we're going to, that red line is our trajectory, and we are going to intercept Pluto, the largest object in the Kuiper Belt, next July, as I said, on Bastille Day. And then the spacecraft, which is flying fast enough to escape the gravity of the sun and fly out into the galaxy, will continue to explore in the Kuiper Belt in later years, in the late teens and in the 2020s. The reason we got to do this was because the discovery that revolutionized astronomy, the discovery of the Kuiper Belt that I just spoke of, the largest structure in the solar system. But more than that, with the discovery of the Kuiper Belt came the realization, through other discoveries of objects in it, that Pluto's not the misfit at all. It's not this weird little planet that's orbiting further out that doesn't fit the pattern of the 4 rocky terrestrial planets and the 4 giant planets. It was simply the first, because it's the brightest and the largest, of a whole sea of small planets that orbit in this third zone of the solar system. It shook us up. We thought we had it down. We thought we understood the pattern of the solar system. We did not at all. In fact, the outer solar system is littered with real worlds with names like Quaoar, Sedna, Haumea, Makemake, Pluto, Eris, and others. They have satellites, they have cores, they have, in many cases, atmospheres. Like Pluto, many have polar caps, and many other attributes that just floored us when we realized that the population of planets in the solar system may be closer to 900 than 9. And don't worry about the names. You don't have to remember their names. I know we live on a planet, we grew up in an era when there were so few that you could name them all. As if you grew up on a desert island, there were only 8 or 9 palm trees and they each had names. And later you discovered there were other islands and more palm trees and you could never keep track. Children of the 21st century won't have to memorize the names of all the planets. They'll just have to know, like they learn about the rivers of the earth or the mountains, the names of the biggest ones, maybe the most famous, and that there are lots more. You can look them up on maps. Isn't it wonderful when we make discoveries like this, that we were so wrong for so long about not just the architecture of our solar system, but the population of it as well. Those realizations are what unlocked $1 billion in taxpayer money to rocket this mission to the top of the priority queue. When the National Academy of Sciences realized, as a part of its prioritization in 2003 of all missions to the planets, that we'd spent almost 50 years exploring and had never been to the Kuiper Belt, this vast new region, this unexplored scientific wonderland. That mission went to the very top of the queue, not the A-list, the top of the A-list. And as a result of that, we got to build this fantastic spacecraft to go and explore these new worlds in this very distant region, billions of miles away, in a new paradigm. And I love this picture of a little girl blowing bubbles that become planets. That planets are as common as the stars of the galaxy, probably more so. I think that makes it all the more special. So we built this spacecraft, which you see as a cartoon drawing in the main illustration here. And in the inset, you can see it with people next to it for scale. You see the dish antenna. It's for communicating with the Earth. you can see our power supply. It's called a RTG. That's what powers all the outer planet spacecraft. Because we're going too far away to use solar arrays. The sun is 1,000 times fainter at Pluto than it is out on the street in Manhattan. Does anybody know what RTG stands for? Steve?
A radioisotope thermal generator.
He's right. It stands for a radioisotope thermoelectric generator. Say that 3 times fast. I call it a really terrific generator because it makes these missions possible. This device, which looks sort of like a hair curler, actually is a thermos bottle that contains plutonium, radioactive plutonium, which, by the way, was named for the planet Pluto, just like Neptunium was named for Neptune and uranium for Uranus. The plutonium inside gets very hot because it's trapped in that metal case. It's radioactively decaying. It reaches a temperature of over 1,000 degrees centigrade, generating about 5 kilowatts of heat. And through devices called thermocouples, we turn some of that heat into DC electricity to run all the avionics, the scientific instruments on board this little spacecraft. Now, compared to Voyager, which many of you have heard about, and which reconnoitered Jupiter, Saturn, Uranus, and Neptune, Voyager, counting its antennas and probes, is about the size of this room. And my little spacecraft's about the size of that table. It's about the size of a baby grand piano. But just like the computer revolution in the 1970s to the 2000s, where we shrunk mainframes and filled an entire room and cost millions of dollars, down into little tablets that have 1,000,000 times the capability and cost tens of thousands of times less. This little spacecraft is a revolution in capability, very similar. It's much smaller than Voyager, but it's much more powerful, much faster, much less expensive. The 7 scientific instruments on this spacecraft combined weigh less than just the camera on Voyager. Yet my camera has 10,000 times the capability of the 1970s Voyager camera. The infrared mapping spectrometer has 250,000 pixels compared to Voyager's 1 pixel. The ultraviolet mapping spectrometer, called ATLAS, on this spacecraft has 32,000 pixels. Voyager's had 2. And I could go on and on. All 7 instruments combined, you turn them on, draw less power than a half of that light bulb. They draw 28 watts combined, including their flight microprocessors. It's really, really a stunning advance in miniaturization. This whole spacecraft and everything on board is redundant. It's like Noah's Ark. There's 2 of everything on board. 2 propulsion systems, 2 guidance computers, 2 command and data handling computers, 2 sets of communications equipment, 2 sets of everything except for the hair curler. Only 1 really terrific generator. And soon now, next year, we'll be arriving to make the first exploration of a new planet since 1989, when Voyager concluded its epic exploration at Neptune. And this picture here, same picture with little circles to help you, is Pluto and its Texas-sized moon, Charon, viewed from New Horizons last summer, still 1 billion kilometers away. This is the best picture that's ever been taken by humanity of the planet Pluto. It's not much. It's taken by the Hubble Space Telescope. What can you tell? Not much. This is the nature of real exploration. We're going to a place that's almost completely unknown. When I talk to school kids, I tell them I've been working on this for 26 years, and I think of Pluto as a present that's been sitting under Christmas tree for 26 years. I don't know what's in the box. We're going to unwrap that present next summer. Take a look at this picture, and let me show you by analogy something else. What's this planet all about? How could you tell? In fact, just like our interpretation of that pixelated image of Pluto, you probably get it wrong. Probably everything we know is wrong. We're not going to rewrite the textbooks next summer. We're going to write the textbooks, because that isn't what you thought. That's what happens when you work with data that's as poor as we have from the Earth, looking 3 billion miles away. What would you know of the Earth if your only image of it was like this, the same resolution as our best picture of Pluto? How would you have any idea of the complexity, the richness, the biosystems, the geology, the weather? How would you know anything from that image? This is the best part of New Horizons. It is going into the unknown for complete discovery. We don't have a fair idea of what to expect. We have no idea of what to expect. And when we get done, the data sets that we're going to have are absolutely stunning. Thermal maps, composition maps. We're going to understand the temperature, pressure structure of the atmosphere, what it's made of and its escape rate. We're going to map all the satellites of Pluto already. 5 are known. We'll probably discover more. We're going to have a chance to look for rings. We're going to, for the first time, reconnoiter a dwarf planet, this new third class of planet. Who thought the little ones were the big deal in terms of the population? It's sort of like we only had a map of the Earth that showed the continents and not all the islands. You had no idea there were all these other landforms out there, just smaller versions of the same thing. So what I did was I asked one of my postdocs, Amanda Zangari, to take a picture taken from Earth orbit of New York City and pixelate it at the resolution that New Horizons will deliver on Pluto. And you see it on the right. So here we are in Manhattan. This picture is about 70 meters per pixel. And if we were looking down on Manhattan with New Horizons from the same altitude that we will map Pluto, you would get this picture. So let's see what we can see. So here's Manhattan, there's Central Park. We're down here. This, if I blew it up further, you'd be able to see better, but you can count the wharfs on the Hudson. Of course, you can see the Hudson and the East River. There's Brooklyn down there. There's LaGuardia Airport. You can see some of the major thoroughfares running north-south. You can count the ponds in Central Park. I'm not expecting to find ponds or Central Park or big thoroughfares and wharfs on Pluto, but that shows you, we're going to go from that smudgy, pixelated picture where we can barely tell it's a world to images with this kind of resolution everywhere on the planet and everywhere on its satellites, and combine that with the other data sets. This is going to be very, very powerful scientifically, and we're really looking forward to delivering it. So I think we can make this work, but I may have skipped a slide. We did. Hopefully we can show you this video about New Horizons. See what happens. It's very short. Well, I think I'll close for Galaxy Forum today by saying thanks again to Steve and by saying something to all of you. Thank you for supporting NASA and the exploration that we do. You should be very proud to know that this is the only country on Earth that's capable of exploring the outer solar system. No one else has even tried. We have 1,000 batting average at this, and we go down in history for it. It's soft power projection in a real way. Textbooks all around the world, whether you speak Arabic or Farsi or Japanese or Mandarin, or whether you speak German or French or Spanish or English, they write about missions like Voyager. They write about our modern knowledge of the solar system. It comes through this American exploration of our future in space. Please mark July on your calendar. We're going to take you on a journey with social media, with film and video, with live television, and with lots of media to the Woodstock of space exploration for the 20 teens. Come and join us for New Horizons at the planet Pluto, July 14th, 2015. Be there. Thank you very much.
Yeah, sure.
Okay.
That was awesome.
I guess Steve says I can answer a question or two, if there are any. Yes, sir.
There's millions of questions, but first one, you're going so far out into space. Can you take pictures of other things along the way, or do we wait till we get to Pluto?
So we're not passing anything except the planet Jupiter that we flew by in 2007. And space is very empty. I think actually that's why they call it space. And so there's nothing really along the way to take pictures of that's anywhere close to where we are. But after encountering Pluto, in the succeeding years, we will go right up close and run right over Kuiper Belt objects to make for future explorations if NASA approves the budget to go on. We have the power and the spacecraft capability, the propulsion to go on.
Follow-up question, how long does it take to get data back that far away?
3 billion miles away, speed of light, do the arithmetic, it works out, it's 4.5 hours. So when the spacecraft sends a 1 or a 0, you know, forming part of a pixel in a single image, 4.5 hours later we receive it on the Earth.
Wow, that's incredible.
Yeah, so one of the implications is this spacecraft is round trip 9 hours from home. Anything goes wrong, it has to take care of itself for that first 9 hours. So we put an artificial intelligence agent on board that acts like a test pilot, that can recognize any one of about 200 separate fault conditions like a fuel leak or a computer reset or low power, things like that, and run down a checklist just like an astronaut would. Yes, sir?
What is the density of this belt?
There are about 100,000 Kuiper Belt objects that are larger than Rhode Island. Only a handful as big as Pluto. Pluto, to give you a scale, you know, it's hard when you see the images I showed you or artist conceptions. And when I say it's 2,300 kilometers across, what does it mean? So let's just talk about a road trip. To give you a feel for the size of Pluto, if you drove around the equator and clocked the distance, it'd be the same as from here in Manhattan to Moscow in Russia. Okay, that's where we're going. However, if you do the math and you take the size of the Kuiper Belt and pepper all those Kuiper Belt objects in it, the little ones that are the size of Rhode Island, the big ones like Pluto, and you ask what's the average spacing between them, it's about 100 million miles. It is vast. In fact, the zone where Pluto orbits is larger than the zone where all the inner 8 planets out to Neptune orbit. It's really an undiscovered continent.
Is it all within the plane of the...
It is, but because the objects are farther from the sun, where the sun's gravity is weaker because it's farther out, the plane gets puffier and puffier. So when you see like Pluto's orbit is tilted, that's a consequence of being farther away on a looser string gravitationally. In fact, around other star systems, we see exactly the same thing. The outer planets are typically on more inclined orbits. One more, maybe? Yes, ma'am.
I'm curious, how much plutonium is being carried, and is that like the future of fueling spacecrafts that are going long distance?
When they're going far from the sun, that's the only way we know how to power them with today's technology. I like to tell people I'm kind of in the waste disposal business because I sent 50 kilograms of Pluto off the planet, 50 kilograms of plutonium off the planet. You know, that plutonium was about half US plutonium that was high graded in breeder reactors in Tennessee, and then conditioned for flight in Los Alamos National Labs, and about half of it came from Russia. So sometimes I tell school kids, you know, if you look at it on a microscope, there's little red plutonium atoms and blue plutonium atoms. But it's amazing, only 50 kilograms of this stuff powers, and so it'll power that spacecraft as long as into the 2040s. Okay, thank you very much, Steve.
Thank you.